So David, if you want to take it from here, you can start sharing your slides.
Okay, thank you, Mariana. Okay, so I'm going to just resume the slides we were going through yesterday. And so that won't take very long. And then we're going to look at the data sets together that you had picked for your homework last night. And so what we'll do is each of us will open up a Jupyter notebook and we'll go through, and I'll just show you what I think are kind of the first things I do when I get a new data set to really understand what information is there and what you can do with the data set. So kind of maybe more hands-on. Okay, so let me see if I can share my screen. Yes. Okay, so we were talking mostly about the data side of machine learning. Remember, machine learning has two main components, the data and the models. And now I'm just going to finish up, focus a bit more on the models. And there's a lot of models that are used by Google and Facebook and companies in industry, but the models that make sense for astronomy are somehow different in important ways. And so I've listed three here. So one really important difference is that for Google, a model is something that can recognize pictures of your ant or your cat. But there's not really any fundamental first principle theory for what pixels correspond to a cat and what pixels correspond to your mother. But the models that we build really are traceable often to some underlying physical theory. It might be an effective theory of galaxy evolution, or it might be something first principles that traces back to quantum mechanics or general relativity. But usually there's really a strong theoretical foundation to the models that we're using, and it makes sense that we should try and build models that we use in machine learning that also have that strong connection to the underlying theory. And another aspect of that is because the models that we're using, they're not just ad hoc empirical models. The parameters in those models are usually going to be quite interesting. And so a model that Facebook uses to detect a spam post or a political post, it might work really well, but the parameters inside that model are just not at all interesting, but they're not even interpretable. You can't make any sense of them. A deep neural network can easily have 1 million different parameters, and none of them really have any interpretable meaning. But the parameters in our models are definitely interesting. Some of them are fundamental parameters related to cosmology, cosmic expansion history. Some of them might be nuisance parameters related to galaxy populations or instrumental effects, but they're still things that are interpretable and interesting. So that's an important difference in our models. Another important difference is that because we care about parameters, we almost always also care about the uncertainties in those parameters. And it's much harder to come up with an uncertainty for a parameter than it is to come up with a good value for a parameter. So we'll talk more tomorrow about Bayesian ways of thinking about things, but really for a Bayesian, it's really the distribution of possible values of a parameter that's important, not just some good single value, what we call a point estimate in statistics. And so it's, although there's a lot of models out there, you can find in papers and find on GitHub, it's pretty rare that models, when people develop a model, they give you any insight in how you can estimate the uncertainties from the parameters. So there are though some models that actually do understand uncertainties both as inputs, and they're often then referred to as weights, and they can also provide output parameter uncertainties. And there's also certain areas of deep learning and neural networks where you can interpret some of the things we do. So for example, dropout, which is a technique where you randomly turn on and off connections in the network. That's actually, dropout has a deep connection to errors in the prediction of the network. So there is some theoretical work to understand the uncertainties and the connections with neural networks. And then the third, I think, important difference is that the physical world that we're trying to model has lots of symmetries, okay, or equivalently conserved quantities, energy, translation invariance as momentum conservation, time invariance is energy conservation, rotation invariance is angular momentum conservation. And so it makes a lot of sense that we should want to use models in machine learning that have these symmetries built in. But that turns out to be surprisingly hard to do. So let's look specifically at symmetries, how symmetries come into machine learning. So there's really no general framework for building a machine learning model that has certain symmetries. And part of the reason for that is there's actually a really easy way to kind of in an ad hoc way impose symmetries. You don't impose symmetries on the model, you impose symmetries on the data that the model sees. Okay, so the model itself has no concept of symmetry, but you just make sure that the data respects the symmetries that are important. So the model can only, it never sees data that breaks the symmetry. And so how does this work? So this is a pretty common technique in image processing models. So here's an example on the top left here. So this is an original, this is an image in our data set. So this is actually something we observed. And then what we do is, instead of training just with that one image on the top left, we also, whenever we feed the model this one image, we also feed it a whole bunch of variations. So I've shown 7 additional variations of that model. And each one is just generated algorithmically from the original. So the one just to the right, we've just flipped the image left-right. So we've applied a mirror symmetry. Over here, we've slightly cropped it, and we've changed the shape of it a bit. Over here, we've done some sort of stretching or shearing operation. Down here, we've rotated, we've zoomed out over here. We can also change the exposure values, so change the brightness or the contrast. So each time you apply some variation to the image, you're basically in an ad hoc way imposing a symmetry on the data. So you're saying by putting in this left-right flip, then you're saying that you want to train a model that behaves the same way when the image has that transformation applied to it. Notice there's one simple symmetry operation does not apply here. We don't apply a vertical flip operation. And that's because photos where people's heads are at the top and their feet are at the bottom are much more common than photos when the heads are at the bottom and the feet are at the top. So this technique is called data augmentation because you're basically, you take one, for every actual row in your data set that you observed, you will feed in many copies. Here I've just got 8, but it could be 100. And it's a relatively simple thing to do, but it's quite expensive because now this means that you need to train the data set that you're training on, that you're feeding to your model, now becomes 10 or 100 times bigger. So it really slows things down. But it's also, fundamentally not a smart way of dealing with this problem, because it would be much more efficient to have a model that knows about the symmetries, because that would vastly reduce the number of parameters that the model requires. So instead, we're saying we're going to make a model with millions of parameters, and we're just going to augment the data so that those to ensure that those millions of parameters respect the symmetries. So there is an important example here, although where we are able to apply a symmetry to a model, and that is something called a convolutional neural network, which will probably be be talking about when you look at neural networks in the other lectures. So although this wasn't really the reason for developing convolutional networks, after they've been used for a while, people realized, well, actually the reason they work so well is because they are translation invariant, because a convolutional neural network just looks at a small local region of pixels in an image. And so they are by construction translation invariant. There's another example of a neural network architecture that has a symmetry, and that is what's called a recurrent neural network, which is actually time translation invariant. And that's the architecture that's usually used to process natural language, so just sentences of Spanish or English. And so the reason that's an important invariance there is because the meaning of a word doesn't really depend on how many words come before it or after it in the text. And just as yesterday, please, if there's anything that's not clear or you have a question, it's good to ask. Is good to ask now. Okay, so Sebastian says CNN is not also rotation invariant. No, no, rotation invariance is much harder to build in. Yeah. So if you use a convolutional neural network, then your algorithm will automatically find the dog. If you've got a big photo and there's just a small dog in it, it won't matter where the dog is in the image, it will find it equally well. But if you apply a rotation, it's much harder. Yeah, it's surprisingly hard. And there's actually a lot of work going on now, being pioneered, I think, by physicists and astronomers to think more deeply about how do we build in symmetries to our models. Because the opportunity there is you'll have a model which has much fewer parameters, and then you won't need so much data. Okay, so at the beginning, I showed you, kind of walked you through the supervised learning loop. And of course, there's two different types of learning broadly. There's unsupervised learning and there's supervised learning. And in some sense, unsupervised is sort of the more natural, obvious way of learning. So what in unsupervised learning, you treat your data, so X here represents your spreadsheet of data with where the columns are the features and the rows are the samples or the observations. Unsupervised learning treats all of this data holistically as just one chunk. So we're not making any distinction between the features. All the features are equally relevant. And so we just learn patterns in this whole spreadsheet. And effectively, if we want to think of this in statistical terms, what we do in unsupervised learning is we're learning the joint probability distribution on all of the features. So if we had three features, we'd be learning a joint probability distribution, P of X, Y, Z. In supervised learning, what we do is we single out one or a small number of features. So we're going to remove, let's say, column C here, feature C. We're going to treat this feature separately, and we're going to consider that as a label of the data. And then what we're doing, the problem that we set up is we try and use the other features, X, Y, Z, A, B, to predict that special feature C. Okay, so we're trying to do a prediction problem. So it's basically supervised because in the training phase, we have the true values of C that are supervising the learning process. So in the language of statistics, now what we're learning is we're learning a conditional probability. We're learning the conditional probability of the one feature, call it C, so the conditional probability of C given all the values of all of the other features. Okay, so it just really boils down to, from a statistical point of view, whether you're learning a full joint probability distribution or whether you're learning a conditional probability distribution. So I would say that a lot of the recent progress in machine learning has actually been in the unsupervised learning area. And a lot of it is potentially quite relevant for physical sciences and astronomy in particular. So what are some typical tasks that we do in unsupervised learning? So one is dimensionality reduction. So, and here the question we're trying to answer is I've got this data, and how can I represent the same data more efficiently with fewer features? Okay, so if I have my data might have 1,000 features, but I don't really think that there is a 1,000 independent, useful pieces of information about every observation. There might only be 100 or even just 10. And so dimensionality reduction is about how can we discover kind of that subspace that really contains most of the information. And we'll look at the when we turn to our data sets. I'll give you some hints on how to start thinking about that using principal component analysis. So we'll be looking at that in a minute. And some terminology. So the new features that you're discovering in dimensionality reduction. So in machine learning, those are usually called latent features, as opposed to the observed features. Another useful unsupervised learning task is what's called generative modeling. And so the idea here is you've observed a small, sparse data set. So this is what you've observed about the world. And what you want to do now is you want to train a model that will allow you to generate random data that's sampled from the same underlying distribution. Okay, so specifically, let's say we're interested in high redshift quasars, and we've managed to, in our DESI observations, we've managed to get spectra of 100 of these high redshift quasars. But now we want to use those 100 high redshift quasar spectra to generate a larger sample. Let's say we want to generate 100 more spectra. So generative modeling is basically about the best way to do that, and that's an unsupervised learning problem. Probabilistic modeling is quite similar, but it's taking a different, asking a different question. And that is, what's the probability that a new observation is drawn from the same distribution as your reference data set? So coming back to the example of the high redshift quasars, so we'll train our model, we'll train a probabilistic model on the 100 high redshift quasar spectra that we've seen. And now let's say tomorrow night we observe a new spectrum and we think it might be a high redshift quasar. So probabilistic modeling will let you use that trained model to give a probability that the new spectra is indeed a high redshift quasar. Okay, so that's another useful technique. And you don't have to just use probabilistic modeling for kind of the rare things like high redshift quasars. You might instead turn it around and use probabilistic modeling for the very common things. So let's say you have just galaxy spectra. You train a model to assign a probability to just a normal galaxy spectrum. And then you can use that to identify outliers, so things that are anomalies. And because they will, when you ask, what's the probability of this weird thing being a galaxy, it will say the probability is very low. And so that's actually really useful because it lets you detect like anomalies, like interesting weird things in the data that you've never seen before. And so that's very useful because you don't normally, when you're using machine learning, you have to have examples of what you're looking for in order to learn about them. And this is, in this case, what you're doing by identifying something as having a low probability of of the type of things you've seen before. You can actually discover new classes of spectra or objects in the sky without knowing in advance what you're looking for. So that's, in machine learning, that's called anomaly detection. And that's something that can be really useful in astronomy. Okay, so here's a picture to kind of show the relationship between these two things: the generative model that allows you to generate new random data, and the probabilistic model that allows you to take new data and assign a probability to it. And so how does this work? So we have the data in blue on the left. That's what we observe. And then we can train either a generative model or a probabilistic model. And the relationship between them is a generative model is something that's capable of generating new random realizations of the data. Whereas a probabilistic model, instead of generating data, it takes data as input and gives you as output a probability. And specifically what that probability is it's the likelihood probability. And tomorrow we're gonna define more clearly things like likelihoods and priors and evidence tomorrow. Okay, the probability that you get out is a likelihood. The way we read this is the probability of the data given the model, which is represented by theta here, which is just the set of numbers, the parameters of the model. And both of the generative model and probabilistic model, under the, inside, they're really the same thing. And so there's a common set of parameters for those two models. There's one other thing I've drawn here, and that is a random number generator, RNG. And so you only need random numbers in the generative model. There's no random numbers required down here. I wrote here reproducible. And the reason for that is that when we use random numbers in machine learning, we don't really want, let's say we had a true random number generator, we probably wouldn't use it most of the time. Really what we want with random numbers, and this is just true generally in scientific data analysis, when we use random numbers, we really want something that's unpredictable by humans, so it basically has no obvious patterns, but we also want it to be reproducible. So it's pretty important when you use random numbers to use them in a reproducible way, so that you can get, when you do an analysis, let's say you make a plot that has some random sample shown in it, you want to be able to generate exactly the same plot tomorrow. And if that plot goes in a paper, you want to make sure that someone else, one of your collaborators, can also make the same plot. So what does reproducible random numbers means? It means you always need to set the seed, or even better, you should use, like in NumPy, there's this concept of a random state, and so you should generally use random states for your random numbers. Okay, so that's kind of in a diagram the relationship between a generative model and a probabilistic model. Notice we have the data on the left and the parameters on the right. But what if we think of the parameters as data themselves? So that looks like this. So notice I changed the box to a circle. And so now we're thinking of the parameters as a type of data, but this is unobserved data. I mean, the parameters are related to the data because the data is what determines the parameters. So in some sense, the parameters are just another internal representation of the data. So we can think of, the data has observed features, and the parameters are just a corresponding set of unobserved or latent features. And with this viewpoint, then, we can actually talk about having a generative model for the parameters. And we can also have, so that would be something that would generate a set of parameters. And so if you've ever used, Planck Markov chain Monte Carlo chains, so if you want to use Planck results to combine with your analysis, you basically download these long chains. But what are they? They're just files that have each row is one set of parameters. So that's basically a data set consisting of parameters. So it's in the unobserved, not the parameters in those files, omega m, things like that, they were not directly observed. They are latent features that were inferred from the actual data which was observed, which is temperature and isotropies on the sky. Okay, so Markov chain Monte Carlo is a generative model for parameters, not for data, or the way it's used in cosmology usually. And then similarly, you can have a probabilistic model on parameters. So given a set of parameters, you plug it in here, and this will tell you the probability of those parameters. And so if it's just so normally we would talk about in Bayesian language, we talk about that probability on the parameters as the prior. Of course, it might also, what we really want is not really the likelihood or the prior. We want the probability of the parameters given the data we've observed, which is what's known as the posterior. And we'll talk more tomorrow about that. So over here in the box, we have the parameters. That's what basically controls the generative and probabilistic model. when we go one more layer, so now we also, our new generative model and probabilistic model have parameters, but we would call these hyperparameters. Okay, so these are those hyperparameters I was talking about before. So again, what's the difference between parameters and hyperparameters? So the hyperparameters are not being determined from the data. So the parameters are determined from the data, but the hyperparameters are not determined directly from the data. Okay, so a lot of the progress in machine learning has come about because the community together have defined some so-called benchmark problems. And this has really helped because if you really clearly define a problem, and then as people come up with new ideas, they keep applying it to this same problem. It makes it much easier to understand, to measure the progress in the field. And so what are the benchmark problems in machine learning broadly? So in general, they focus on tasks related to vision. So basically algorithms trying to do the same thing that we do with our eyes and our brains, and also on natural language tasks. So again, algorithms doing the same thing that we do with our ears and our mouths and our brains. And so it's things like, given a set of pixels in a photograph, is that a photograph of a cat or a dog? If it's a dog, what breed of dog? So that's kind of a benchmark problem. Another thing is when you have a complex image of a street scene, for example, where are the people, the cars, the street signs, the traffic lights, for example, and that's becoming very relevant for self-driving cars right now. In natural language, how do you translate a phrase from, if you have a phrase in Spanish, how do you translate that into English or Chinese? If you have a review of a restaurant on Yelp, or a review of a book on Amazon, is that a positive review or a negative review? Okay, that's known as sentiment analysis. So these are all benchmark problems. They're the kind of the same problems that a lot of people independently are working on. And because people keep working on the same problems, it's easy to measure progress in the field. So a really efficient way to get started, if you're thinking about how do I get started in using some machine learning in my research, is you want to think about problems in your research which map as closely as possible to some of these really well-studied benchmark problems in machine learning. So, I don't think any of us really need to be able to tell the difference between a cat or a dog in our photos, but maybe it's useful to be able to tell the difference between a star and a galaxy, or a quasar and a star. Okay? So that's a pretty similar problem. And once you recognize that similarity, then you know that you really need to now look at the literature and what is the state of the art for telling the difference between cats and dogs, because that's really going to be your best starting point for telling the difference between stars and galaxies. So. And really what has made these benchmark problems so useful is it's not just defining the problem, but it's also defining a standard data set that everyone uses to evaluate their solutions to the problem. And so this is something we're really missing in astronomy. There's a lot of work going on now in applying machine learning to astronomy, but we don't have these standard these benchmark data sets. So these are data sets that are public, they're relatively small, anyone can download them, they're really well documented. There's tons of papers that use them. And so, the classic paper, or the classic data set in this area is something called MNIST, this is an example of a single observation in an MNIST sample. So it's just grayscale square images, pretty coarse pixels. They're just 23 by 23 pixels, and they're handwritten digits. And so there's only they're labeled. So the true labels for supervised learning is either 0 through 9, just the 10 single digits, and there's only 70,000 of them. So whenever someone comes up with a new technique for a classification problem, you always have to first just test it out on MNIST. But MNIST doesn't really, now there's so many methods that can get basically perfect scores on MNIST. So we need harder harder problems. So the next harder one is something called CFAR 10. So there's about the same number, 60,000 of them, and they're just a little bit bigger. Here's an example over here. So it's not a very good photograph, but you can still tell that there's a dog there and some yellow flowers. In fact, it's probably a puppy. It looks kind of like a young small dog. The reason it's called CFAR 10 is there's only 10 different categories. Okay, so that airplanes, cards, birds, and that, so on. Okay, so it's a pretty kind of idiosyncratic data set. So if you develop an algorithm that does really well at this, it's really not that useful, because it can't identify anything outside of these 10 categories. But it's still useful as a community to have really well-defined problems to benchmark progress on. And then sort of more the state of the art. This is what that competition I was showing you about, the scores from the back here. These scores here were from the ImageNet competition. So now I'm showing you the ImageNet data set. So there's about 200,000 of these. They're much bigger, and they have actually different sizes. And these are labeled not with 10 categories, but with 1,000 categories. In fact, those 1,000 categories include 90 dog breeds. So algorithms that do well on ImageNet problems are remarkably good at identifying different breeds of dogs. So here's an example of this. So you see, we really, this is quite challenging because what the individual features here, right? So there's a look at the number of pixels here. So you kind of got tens of thousands of pixels, and each pixel is actually 3 numbers. Okay, so there is on the order of 100,000 features in each observation here. So if you think of that as a data set, take this 2-dimensional. This is really a 3-dimensional array. We have X, Y, and then the color RGB. So flatten out that NumPy array, and so that's one row of your data set. So it's a really wide, lots of features here. But the features have very little information on them individually. Okay, there's plenty of pixels here, which individually contain almost no information about whether there's a dog in this image. Okay, certainly the background pixels have no information. Maybe the pixels over here, the fact that the color is a sort of a possible color for a dog fur, that gives you some information, but it's a really low amount of information. So it's actually quite a challenging problem to just go from raw pixels to identifying what's in an image with 1,000 possible categories. Okay, so how do we fix this? The fact that we don't have these really useful, curated, well-documented data sets. So, I mean, I encourage you, as you're starting to use machine learning in your research, to build your own public data set and share it. In fact, my university, UCI, hosts one of the main repositories for these shared data sets. Okay, so to finish up, kind of want to give you a little perspective, or my perspective, which will kind of set up what we'll talk about tomorrow. So what do we think the language of machine learning is? Okay, is it C++, Python, JavaScript, Swift? There's a lot of different languages that people use for machine learning. Now, all of these are used pretty heavily. Like TensorFlow is mostly written in C++ and PyTorch as well. Most people doing machine learning are using Python. An increasing amount of machine learning is done in the browser, and that's all done in JavaScript. For a while, it looked like Google was going to go entirely to using this new language, Swift, for machine learning. But I think they've abandoned that. Okay, but really the language of machine learning is not a computer language. It's a human language, and it's basically a mathematical language. It's a language of statistics. So here's just a brief excerpt from a classic machine learning paper, Kimmer and Welling, Autoencoding Variational Bayes. Okay, so if you've heard of, there's a deep neural network architecture for unsupervised learning called a VAE, or Variational Autoencoder. And so this was the paper that introduced it. It has lots of citations. But if we just pick a small section from the first page, okay, so this is how people in the field talk about the work they're doing. Okay, so there's no code here. There's no Python, no C++ here. Okay, this is very mathematical, and it's really all about probabilities and statistics. Okay, so we have X and Z. X is the observed random variable, Z are latent random variables, Q and P are probability densities. This thing here, KL, the KL divergence is a way of measuring the similarity between two different probability densities. And here we have the script L, that's the likelihood. We have expectation values here. So it's all statistics. Okay, so it's really, if you want to really get more immersed in the literature of machine learning, probably if you're like me, you've never taken a formal class in probability theory, but hopefully just this quick snapshot convinces you that it is important to really understand the literature, and especially if you want to go on and develop new methods and be able to kind of read the new literature in machine learning. So we will look more and talk more about the statistics and probability tomorrow. Okay, so at my university in Irvine, I teach a 10-week course, so a full quarter on it's called Machine Learning and Statistics for the graduate students in physics and astronomy. And I put a link to the table of contents. The whole course consists of Jupyter notebooks on different topics, but I wanted to just kind of give you a roadmap just to show you kind of what I think the important topics and examples are to cover if you want to spend more time learning about this. So we've basically done today and yesterday what's up here. We've talked in some depth about data and models and how they interact and are the foundation of machine learning. And so then in this course, we spend roughly a third of the time on unsupervised learning and focusing on two applications, clustering, which I didn't mention, and then dimensionality reduction, which I did talk about earlier. And then we spend the next third of the course on supervised learning, so looking at regression and classification. And the distinction between regression and classification is just whether that one column of labels that you pick out to learn, whether it's a real valued, a numerical feature, in which case we call that regression, or whether it's a classification. And we're actually going to see a simple example of doing the regression and classification in the Jupyter notebooks in a minute. And then finally, we talk about kind of a third type of learning, and in order to talk about this, we spend some time really learning about probability theory and applied statistics. And I call this inference learning. And really what this is about, it's about how to do practical Bayesian computation. And we'll talk more about tomorrow about why Bayesian. It's easy to kind of set up a question or to ask a question in a Bayesian way, but it's actually quite hard to answer it in a practical computational way. And so there's two really important techniques for solving, doing Bayesian inference. So one is Markov chain Monte Carlo, and the other is known as variational inference. And so for all of these topics, there is if you go to this table of contents, there is kind of detailed notebooks with with all the examples that you can run yourself on these topics. Okay, so with that, so I'm going to end these slides now, and it's time for some questions. And then what we're going to do next is we're going to open up, each of you can open up a Jupyter notebook, and we're going to go through your data sets together. And I'm going to show you, kind of walk you through what the first steps that I usually do when I'm working with a new data set. Stop sharing, and we can just take a minute for questions now. I see there was a question in the chat a while ago from Sebastian about Galaxy Zoo. Yeah, so I didn't see when that came up, but I'm guessing that you wrote that when I said we don't have standard data sets. Right. So yeah, so Galaxy Zoo is a good example. So I mean, the purpose of Galaxy Zoo is not really for training machine learning models, although now people are starting to use it for that. The purpose of Galaxy Zoo is to get crowdsourced classifications. It's basically to generate human labels for machine learning, and that's been very successful. But that's a good example. Unfortunately, I don't think the organizers of Galaxy Zoo that's their main focus, but it is probably one of the best examples. So I have seen some interesting work on, so I work on DESI, but also on LSST and the Dark Energy Science Collaboration. And the main topic I work on in Dark Energy Science Collaboration is the blending of galaxies together. So where two galaxies are so overlapping that it's hard to measure their shapes for doing relensing, which is a problem if they're at different redshifts, because they're really probing different parts of the different redshift ranges. So there was an interesting paper a while ago that it was a machine learning, a convolutional neural network, I think, using training data from the Galaxy Zoo. But the problem is that the images that the Galaxy Zoo provides are JPEG images. Okay, so JPEG images are not good for scientific applications because of the compression that they use. And so JPEG images, really the algorithm is designed to throw away information that human perception doesn't really notice. But machine learning, a neural network is very different from human perception. And so the artifacts that JPEG compression introduces are very noticeable to a machine learning algorithm. And I'm pretty sure that the good results that paper got are at least in part due because it was learning to detect JPEG compression artifacts rather than really useful things in the scientifically relevant data. We should, PNG is actually a good compromise because it's something that you can display in the browser easily. It's relatively efficient, and it doesn't. You can use you can store PNG images without any compression. But of course, since astronomers, we love FITS files too. Good. So any other questions? And I'm happy, if you think of something later on, I'm happy just to post a question either to me directly on Slack or in the channel that we have set up. Has anyone actually tried to put together a reference data set for a problem that they're working on? It doesn't need to be huge. If we look at the data sets that are used right now, so MNIST and CFAR10, they're less than 100,000 images. So it doesn't need to be something massive. I'm hoping, so I saw you're going to talk about getting involved in Dark Energy Science Collaboration later in the week. So one of the things that the Dark Energy Science Collaboration has done is done a pretty large scale simulation. So it's called a DC2 or Data Challenge 2. And I think the data is now public. So even if you aren't a member of LSST, you can access that data. And so I think there's really a lot of potential. I mean, it's a huge data set, lots of FITS files, but I think there's ways of generating from that some useful reference data sets for machine learning. So, and it's basically trying to simulate a reasonable, not the full 20,000 square degrees that LSST is going to observe, but it's a pretty large patch of the sky at to 10-year depth of simulated LSST observations. So. Okay, so I think since I don't see any more questions, so now let's have everyone open up a Jupyter notebook, and I put some notes that could be helpful to follow along in the README on our GitHub repo. I'll just put a link to that in the chat. Again, and you can see that I've got that up here now on the screen. Okay, so so I asked you yesterday to pick a data set, so a lot of you did that and entered them on this the spreadsheet that that I gave you. In case you didn't have a time to pick a data set, there's three I also included in the repository. One is on COVID vaccination rates, but also merged with some just general United Nations indicators for different countries of the world. Another, if you're following the Euros like me, so another one is about player statistics for there's too many players, so I just limited it to the Spain, Italy, France, Germany, England, and Mexico first divisions. And then the last one is kind of a classic machine learning data set on the passengers on the Titanic. So you can, for example, see if you can predict which passengers survived and which ones didn't. So hopefully you were able to get a Conda environment set up where you can import these packages. So if you weren't able to do that, well, I mean, any environment should have NumPy and Matplotlib, the first two installed. And all we're really going to need today is pandas in order to be able to load your data set. But the other ones will let you do a bit more. So I'm just going to copy that, and then here, move to this tab here where I have a notebook open. So this is a new notebook, and I'm just going to so just follow along with me, and then I'll show you where we want to enter your own data set. So it's useful when you start your notebooks always to have kind of a standard preamble, the things that you do at the beginning. So I usually just tell Matplotlib using this magic command with the %sign that we want to have our plots in line, and then I'll paste in those imports there. Okay, and in case one of these doesn't work, so let's say you weren't able to install Seaborn, then just comment that out and run it again, and you'll just have to skip the sections that use Seaborn below. And I'm keeping an eye on the chat, so just let me know there if there's anything, if you have any questions, or you can just jump in as well and ask your questions. Okay, so the first thing we're going to do is we need to read the data. And as long as it's in a format that that pandas can read, and pandas has a whole bunch of those different read underscore for different formats. And so, some of them are quite compact binary formats. So like the HF5 format, that's what I usually use if I've got a big data file. For smaller data files, where there's a mixture of text and numbers, or more heterogeneous data files, I usually use a CSV. And sometimes I also use JSON if you want to have a bit more hierarchy to your data files, because those can have more complicated data structures. So for my example, I'm just going to read the COVID data set. So the way I'm going to do that. So I've used pandas, and I'm just going to read CSV like that. Let's say you don't have a data set already loaded. So you can, for example, just read directly from GitHub, one of the ones that I suggested. So if you want to follow along exactly what I'm doing, then I'll just paste into the chat the command you would type. Okay, so this is, you don't need to download the file. This will just, Pandas has a nice feature that if you give it, instead of a local file name, a URL, it will just download it in the background for you. Okay, so I'm going to keep going. I don't see any questions. So the first thing we need to do are just some basic cleaning of the data. And you can spend a lot of time on this. And this is really, in data science, this is what you spend most of your time on. It's really just getting the data into a usable format, especially when you're drawing data from different sources. And so the most basic thing we need to do, though, is we need to remove any rows that have invalid data in them. So for that, I'm just going to say, I'm going to take my original data frame, the DF stands for data frame, and use this method called drop NA. I'm not sure what N, so you normally talk about NaN, which is not a number for floating point values. And I put links to the documentation for the main tech methods that I'm going to show you back in the README here. So right down here, so I have day 2. So drop NA here is, so remove rows with invalid data. So we can, for example, just open up that link to see what it says. So it says remove missing values. It doesn't actually tell us what NA stands for. And there's different ways you can do this. So I think just by default, it will, if a row has a single feature with an invalid value, it will remove that whole row. If there's a row you don't care about, you want to do something a bit more refined, or you might need to do that if a lot of your rows have missing data. But this is kind of just the brute force. This makes sure that every single number in our spreadsheet of the data is valid. Okay, so now we have our data set, so we can just we'll just enter it like that, and we can see, so Pandas does a nice formatting of the data. So we can see there's country, total vaccination, so a bunch of kind of vaccine related stuff. But when I prepared this data set, I also merged it with some just kind of United Nations indicators, so fertility rate, health expenditures, things like that. Okay, so so the purpose of this data set then is to allow us to explore relationships between vaccination rates, and here we also have some Booleans, true, false, for which vaccines are being used in different countries. So to just explore relationships between sort of economic, social indicators and vaccination. Okay, but that's, notice there's a ... here, so we don't really see all the data here. There's also a ... over here, so we're not seeing all of the features. So, you know, this gives you kind of a flavor of what's there, but a better way to look at it is what if we want to pick out a particular, you know, a small subset of features, so we can, unfortunately, indexing in Pandas is a little strange, so you often have to use this thing iloc, rather than, you'd think that with numpy arrays, we would just go like that. And so iloc, so what I'm doing here is I want to just pick out a few countries. So I'm going to say, pick out Mexico, United Kingdom, that's where I was born, and then United States. And I want to see just the first 15 features. I do that. Why United States didn't show up. Okay, so here, for example, so we have Mexico and United Kingdom. So we can see that you know, both England and Mexico are using the AstraZeneca vaccine. Mexico is using Sinovac, and the United Kingdom is not. Information like that. And in general, a good way to get a quick overview of your data set is to use the info method. So you just, whatever your data frame is, and you say .info. So this prints out a list of all of the features in your data set. So we have quite a lot. So we have 57 different features, and then it gives you a sort of a summary here. So it tells you there's 167 entries, and this number here tells you how many of them are non-null, and then, so, you know, valid. So all of them are valid because we did that drop NA earlier. And this will also tell you what type of feature it is. So we have noticed there's a bunch here which are Boolean. So these are just for each type of vaccine, whether it's used or not in that country. And then the numerics, depending on whether they have something after decimal point or not, are coming out as floats or ints there. Okay, so there's a lot of stuff which is not numeric. So, and for most machine learning algorithms, can't really work with strings. And so we want to be able to restrict our data to just the numeric values. And so the way to do that is Pandas has a simple method called select D type. So D type stands for data types. And so we just say we basically want to just restrict ourselves to the columns of our data set, which are numerical. So things that we could use in those machine learning algorithms. And then I'll just add the info of that to list those. Okay, so there's only 26, which are just straightforward numbers. So it's thrown away all of the Booleans and the strings now. And so we'll generally want to do that because to get a kind of a quantitative assessment of our data, we don't really have any way of making sense of the strings that are in the data set. Info is a useful method, but also describe is a useful method. So describe, what it does, it will actually also filter out only the numerical features, and it tells you for each feature, it gives you some basic statistics, the number of entries, the mean, the standard deviation minimum, the maximum, and some percentiles as well. So this is a kind of a useful way of just getting a quick numerical overview of all of the features in your data set. Okay, so that's generally the very first thing I do. If you want to convert once you've got your data set into Pandas format, it's useful to be able to save it in another format. So for example, I can save this data set to CSV. Usually when I save to CSV, usually Pandas has this annoying index concept. So it treats one of your columns as a special index, which is useful if you've got a really big data set, because it's very efficient to do searching and sorting on that data set. But generally, I try and just disable, ignore the index features of Pandas. So that would then just write on my local disk. So for example, if you downloaded the COVID data set from the URL, this is how you make a local copy. And you can also change the format. You can change this to a HF5 or CSV or JSON, whatever you want. Okay, so far what we've done is we basically just looked at text descriptions of our data. So now let's start doing some visual exploration of our data. So for that, we're going to use Seaborn. So Seaborn was this visualization package that's built on top of Matplotlib that we installed here. And really the only reason I use Seaborn is because it has a convenient implementation of some useful plots to get a quick look at some data set. In particular, there's this thing called a pair plot. And so I put a link to that here. No, I didn't. I'll add that link later. So a pair plot, let me just show you a pair plot, and then you'll see, I'll explain what it is. So I'm just pasting that in. I can't type that quickly. So what I've done is I've just picked out two different features. Actually, three different features here. Okay, so let's see if we can understand what's going on here. So we have two numerical features: the people vaccinated per 100. So you'd normally expect that to be a number between, if no one's vaccinated, it'd be at 0. If everyone's vaccinated, it'd be 100. Okay, we actually see one here that's more than 100, so that's a little fishy. And so that's telling us that there's probably more cleaning we need to do to the data. And the other feature we're looking at is the urban population. So what fraction of the total population lives in big cities like Mexico City or Los Angeles. But then the data is further split along with another feature, but that's indicated by the colors. And this is a categorical feature. So it's just whether that country is using the Pfizer vaccine or not. So if they are, it's orange, and if they're not, then it's blue. And so we actually see then some interesting structure. So the countries where very few people are vaccinated are mostly not using the Pfizer vaccine. We can conclude that. There's a small bump where they are. And then conversely, the countries where Pfizer vaccine is being used have a vaccination rate of around 50%. And then maybe there's a correlation we're seeing here between the urban population and so countries that are more urbanized are also more likely to be using the Pfizer vaccine. So we're kind of just getting a visual overview. You can here, you don't need to list the variables that you want. If you want, you can just leave this off. So just remove this entirely, and it will make a pair plot of all the features in your data set. Unfortunately, pair plot is really slow. It will work, but also you're going to have so many, because how many rows and columns do we have? We're going to have 26. So instead of being a 2 by 2 matrix of plots, it'll be 26 by 26. So pair plot's not really so useful if you really want to look at all the features. So you already need to know sort of which features are interesting to look at together to use a pair plot. Here's a different pair plot we can do. So now I'm looking at the daily vaccinations per million, and then seeing if there's a correlation between that and the number of seats held by women in national parliament, so as a percentage. And the first thing that jumps out, well, we see also some kind of interesting bimodal structure again here, but notice here we have a percentage that's minus 100. So this is another example where clearly we need to do some more cleaning on the data. We might say, well, we should just throw away all of the countries that reported a negative percentage, but it's probably better to go back to the original source and figure out why that's happening. And sometimes what you can do is just use the average. If you have some invalid data, you could just use the median of the average of the data set for that. I see Alma has her hand raised. Did you have a question?
Yes, what if we don't have any Boolean variable or categorical variable to do these splits?
So are you asking whether we can include it in the pair plot?
Yes.
Well, we are really, because that's what the color coding is. So, but you can only do that with one variable, unfortunately, though. Yeah. So this is not a great way to really get. This is not a great way to kind of get an overview of the. So it'd be nice to see sort of just a table of, for example, of all the different vaccination booleans. So yeah.
So my question is, in this case, the variable that you're using to color,
yeah,
is a Boolean one,
correct?
Right? And what if I don't have any Boolean or categorical variable, and I just have continuous
sure, right? Okay. So in that case, you can just leave this off. So this is just an option. So I can just remove that entirely. So and then it will just everything is one color. Yeah.
Yeah. Well, I guess my question was if I can find a way to separate the populations according to a third variable, but that is not of this type of Boolean.
Okay, yeah, no, I understand what you're saying. So yeah, so we could do that. What we'd need to do is we'd need to make a categorical variable. So we could add a new variable. So we could add a low population variable, which we would then just say population in thousands. Less than I don't know what we want. That would be 10 million. So now that's a categorical variable. So I can now use that to so that's an example where you could just make a cut on a numerical category to do the coloring. So I see Luz Garcia has a question.
So
yes, thank you.
Yeah, I think there is a question in the chat also. Also you, Luz.
Yeah, just wondering if you think that after you do this new cut and turn this distribution into a categorical sample or subsample, you think it's necessary to save this new data frame, or it's better to keep working with the overall one and just look at the distribution of this particular category that you just created?
Yeah, that's a good question. So mean, I think at this phase, you're doing exploration. So you're not really sure. What you want to be able to do is like quickly try different things. Like, I have a hypothesis that low population is a useful indicator, a Boolean indicator. But as long as you're working in a notebook, then you're going to have sort of a notebook is sort of like the old-fashioned logbook where I used to write everything down on paper and pen. And so you really have that log of what you did. And once you kind of get to the end of that, then you should probably kind of think, well, what really turned out to be useful, and then you could add those as new features. And you can always, again, at that point, just you could write a new. I know I've added to the data set, and I can save it. Oops, to CSV. There we go. Yeah, but I recommend that you don't. You've got your notebook. Your notebook shows how to reconstruct all of the experiments and the plots you made, and then kind of wait until you don't want to get slowed down in that exploratory phase. So I would just wait until a little later before you decide what permanent changes you might want to make. So. Okay, so let's see. So there was a question or a comment from Sebastian. The Gaussian kernels are very large. Yes. Okay. Right. So, yeah. So Sebastian noticed that this is not really a histogram. This is actually something known as a kernel density estimate, which is an unsupervised machine learning method to take an empirical sample, these sets of points, and estimate a continuous probability density from them. And so you're right. So what they're doing here is basically replacing each point in the histogram with a Gaussian, and it's too wide in this case. And yes, there are options to do that. And you can also turn it off, which actually is what happened by default earlier. And you can also, if you want, get a two-dimensional kernel density estimate in the scatter plots as well. So. Yeah. Okay, so next thing we're going to do is now we're going to get a bit more quantitative with our data. So I'm now going to just make a new data set. So originally it was called DF for the whole data frame. And now I'm going to just only keep the features that are numerical. So I'm going to use that select D types again. If I do info on this, we'll see we've only got the numerical, so either integer or floating point values. And the other thing I'm going to do is I want to scale all of my numbers to be to have a mean of 0 and a standard deviation of 1. And the reason I need to do that is because the scales. I mean, right now I've got some things which are surface area in square kilometers. I've got population in thousands. I've got percentages. I've got ratios. So the scale of these things is all over the map. Okay, and so that's going to cause. I mean, it's fine if I know, if I use these things carefully, and if I want to make plots, I really want to show the original values here. But once I'm going to start feeding these into machine learning algorithms. The fact that you can't really just use a Euclidean norm to compare two different countries when you have things in petajoules and kilometers squared. So that's going to be a problem. And so the brute force way of dealing with that is to just force everything, calculate the mean and the standard deviation of each column, and then you're just going to do x minus mu over standard deviation. So that's what this function here is doing. And what is pre-processing? That's something we imported up here. So we're using now the scikit-learn package. So we imported several modules, and pre-processing is the first of those. Okay, so I'm calling that PP data for pre-processed data. Okay, it's very quick. And now what I want to do is I want to get a feel. So I've got, how many features do I have? I have 26 numerical features. So how many of those features are really necessary to describe the data? I mean, some of these are probably pretty highly correlated with the other ones. So this is a type of unsupervised machine learning, which is known as dimensionality reduction. We want to estimate what is really the true number of independent degrees of freedom in these 26 features. And so the way I usually do answer that question as a kind of a quick first look is to use principal component analysis, which is something we've been using in astronomy for a long time. So I'm using now the decomposition model from scikit-learn. I'm building a PCA model. I'm not putting any of the options in here, but there are lots of options. I'm pulling up the help here. So the most important one is the number of components. We were talking about hyperparameters before. So anything that you put in the constructor of a scikit-learn algorithm, those are hyperparameters because they haven't seen the data yet. Okay, so those are things that you're choosing without seeing the data. And then after we've built the PCA algorithm, then we fit it to the data. Okay, so these are hyperparameters. Anything you put here, those would be parameters. Okay, so scikit-learn is nice because it basically, everything has the same kind of structure. You have a module, so this is decomposition. You have an algorithm, PCA, and then once you've built the algorithm with its hyperparameters, then you fit it to the data. Since this is unsupervised learning, we just provide the data in one big blob. If we were doing supervised learning, we'd also here have some labels. And we'll see an example of that in a minute. Okay, so PCA, so there, very quick. I've done a full PCA decomposition. Since I didn't specify the number of components here, what it does, the default is to use all of the components. So now let's make a plot to summarize what PCA is telling us. So what I'm plotting here is, once I've done the PCA, it has a NumPy array called explained variance ratio. And so what this says is for each of the components, so there's 26 components because we didn't restrict it here as a hyperparameter. And so it tells me for each of the components, what fraction of the variance in the data is explained by that component. And then since I did this cumulative sum with NumPy, then it shows me as I add more and more components, how close I get to explaining 100% or a ratio of 1.0 of the variance in the data here. And so so looking at this, I could say, if I can explain 90% of the variation in my data just using 10 components. Okay, and there's 26 components in all. So that means there's basically a subset, a 10-dimensional subset in my 26-dimensional feature space that explains most of the covariance in the data. So I see a question from Sebastian. How many points are recommended to use the PCA methods? So, I mean, you have to have enough data just to formally, in order to determine the principal component decomposition. But that's basically the number, the size of your data set needs to be, the number of elements in the covariance matrix needs to be less than the number of values in your data set. But that's a pretty low bar. And your question about random matrix theory, so that's actually not something I'm familiar with. I'd be interested to learn more about that. Maybe if you have a reference on that, you could post it in the chat or on the Slack. So as I said, so this is often one of the first things I do with a new data set is just to get a feel. So if this was a straight line, that would be saying that basically every feature has an equal amount of information. And so there's no, you're not going to be able to find, to throw away some number of features and preserve most of the information. Really, every feature adds the same incremental information here. And so if you're not familiar with PCA, so I put in here a link. So one of the notebooks on that 10-week course that I described is all about measuring and reducing dimensionality. And in particular, there's a picture there, which you probably find quite helpful, which is explaining what's going on here in terms of linear decompositions here. So PCA is just a linear decomposition technique. You've got your data set here on the left, and you're trying to represent it approximately as a product of two matrices that are that have different two rectangular matrices with different shapes. So how do we extract those two matrices? Well, first let's look at the shapes of things. Oh, I need to, yes, sorry. First, I need to extract those two matrices, Y and M. Okay, so what I'm doing is I'm basically I'm using the PCA to write the matrix of my data, which is 167 observations and 26 features, as a product of these two matrices. Okay, so the first one has the same number of rows as, so it has one row per sample. Oh no, that's the reason that's bigger is because I haven't restricted the number of components. So let me do another fit now, where I'm going to notice that if I have just 10 components, that explains most of the variation in the data. So now I'm going to specify this hyperparameter, say I only want 10 components. So I'm going to redo my fit, make these matrices, and now, so basically now I'm able to approximately describe my full data set as a product of a data set with only 10 new features. So these 10 features, it's not picking 10 out of the original 26. These are 10 linear, orthogonal linear combinations of the 26. And then another matrix which tells me the how to transform the original 26-dimensional feature space into the new 10-dimensional feature space. So this is basically like a projection matrix from the full feature space to the smaller feature space that explains most of the data. Because principal component analysis is an unsupervised learning technique, we don't really have any well-defined problem. We don't have a target or a loss function that we're trying to optimize. And so we don't really have a way of really determining, so we don't really have a well-defined notion of information in this data set. And so in unsupervised learning here, what we're using as our proxy for information is variance. So we're basically saying that the variance or covariance between two features is the same as the information. And that's not necessarily true, because one of the things, especially in scientific data, that creates variance is noise. Okay, so if you've got very noisy data, PCA cannot tell the difference between noise and then actual covariance, because there's interesting relationships between the data. Could you replot to see the improvement? Oh yeah, so in fact, if I replot, it's going to look exactly the same as this original plot. It's just going to stop. It's only going to show me the first 10. So let me show you that. So it doesn't go any higher because we haven't, basically all we've done is we've just truncated we've thrown away all of these last 16. So we end up at the same place. But the important point though is that now we have a way of explaining that 90% of the variance just using those 10 features. Okay, so if Y and M, those two matrices, explain our data, then we should be able to reconstruct our data. So here I'm making a reconstructed data set. What's the shape of this reconstructed thing? It's the same. It's the same as the shape of my original data. They're the same. So using only 10 linear combinations of the original features, I'm able to reconstruct the data. So let's just make a plot to see whether, how well that's working. So here I'm plotting just the first country. I'm not sure what it is, but let's have a look. First country is Afghanistan. Okay, so we're plotting Afghanistan. And I'm going to plot it with dots for the original 26 values. And then with x's for the reconstructed. So if only by just using only 10 linear combinations of features, I'm able to reconstruct all 26 features with the x's. So for some of the features, it's doing really well. In others, it's not so good. But overall, it's doing a pretty good job. And if this wasn't good enough, then I would just need to increase the number of components that I use. So I only use 10. But I could go further. So you have to use some judgment in how far you want to go here. But it's just helpful to just have a kind of a reality check of how you're doing on the features. Notice that these don't really look like percentages and populations and surface areas, and that's because we did that standardization. Okay, because up here we subtracted the mean and then divided by the standard deviation. Okay, so so now we've got a sense that our features there's some redundancy in there, and roughly the dimensionality of our data is more like 10 than 26. But we don't really know which features are important. We could, if we think variance is a good proxy for information, we could take those 10 linear combinations from the PCA and work with that. But usually what I'll do next is I will look at a supervised learning problem. And so for that, I'm going to need to separate my training data from my target data. So for my training data, I'm only going to use the UN indicator. So that's starting at feature 24. So there's no vaccination data there. That's what, by throwing away the first 24 features I'm getting. I'm again also only using the numeric values. So these are the things I'm going to try and I'm going to train on. So surface area, population, GDP, just the different economic, geographic, social indicators. And now the thing that I'm going to try and predict is the percentage of people that are vaccinated. Okay, so that's my target. This is a real value target. So this is a regression problem rather than a classification problem. And so we could train a neural network with this. You'll learn how to do that later. But normally what I start with, just to get a benchmark, I think it's really important before you start using fancy machine learning techniques, just to get a benchmark with something pretty well understood and interpretable. So for that, I use a random forest. And since it's a regression, it's a random forest regressor. So this is the same pattern. This comes from the ensemble module of scikit-learn. Here is my, I'm instantiating the class. Anything I put here would be a hyperparameter. So there's there's a bunch of those which you need to learn about. And then now I'm feeding it to the data. I need to actually give it both the training data and the target values. And so by making a supervised learning problem, we're no longer relying on something like variance as our measure of how much information and what's important. We specifically are trying to predict the target value. So that gives us a much more quantitative and reliable estimate of how well we're doing. So there, it takes a second or two to train the random forest. So to get a sense for how well we've done, so we're trying to predict the vaccination rates from all of this national indicators. So with a random forest, you can just get a score number. And this is the thing that's actually being optimized, what I called the loss function before. So we're getting 0.95. Well, what does that mean? So what this score is it's something called the coefficient of the determination. And in statistics, that's known as R squared. A value of 1 means that you have perfect accuracy. Okay, so being 0.95 is really good. A value of 0 is what you would get if you just took the average. Okay, so if we take the mean target value, so 26 out of 100 people are vaccinated on average over all countries. So if we always predicted 26 for all countries, then that would give us an R squared score of 0. So that's kind of sets the endpoints. You can actually do worse than 0 if you if you have an algorithm that's worse than just guessing the average. Okay, so this is actually doing really well then. That's a high R squared value. But then we want to know, well, which features are actually important? Of all of these 24 features here, which are the ones that are helping us, are most important in predicting the vaccination rate? And so the nice thing about a random forest is, unlike a neural network, it's very interpretable. And one of the things I like to do is with a random forest is measure what's known as the feature importance. And so that is, it basically will give us a score that says how important on a scale of 0 to 1 is each feature. And the way it works is that it takes your data set, your spreadsheet of values, and for each column, in turn, what it does is it just shuffles the entries in that column, okay, while leaving the rest of the spreadsheet the same. And then it redoes the algorithm, whether it's a random forest or a neural network, and it just sees how much does your score decrease. So this R2 score. And so a feature that's really providing no useful information, if you shuffle that column, so basically you're breaking any correlations with other features, it won't make any difference. And the features that are most important, you'll suffer a lot. You'll see a big drop in the R2 score. Okay, so there's a special module in inspection which has this type of algorithm, and then using the permutation importance. So permutation is just referring to the fact that you're shuffling it. Okay, so how do we visualize that? So I'm just going to paste in the code I usually use to visualize this. So I'm telling it, I'm picking out the means of the importance. And if we just look at the plot, so we've listed here all of the features, and it's very clear that there's a single feature that very strongly correlates with the fraction of a vaccinated population. Not at all surprising, it's the GDP per capita. Okay, and then a far distant second is the urban population, the fraction of people that have cell phone subscriptions and so on. But really, this is all driven by one feature. And so this gives us a lot more insight than just doing the PCA, because the PCA was really just looking at variance in the data. And here we're really benchmarking on a specific, a very specific metric, which is how well can you predict this one feature. And so if that's what you really care about, then this feature importance is a very quick way of understanding which features are most important. So sometimes it'll turn out there's really one feature that's doing most of the prediction. And so in that case, you could probably come up with a very simple model, just a linear or nonlinear model predicting the vaccination rate just in terms of this single feature. Okay, and that might be good enough. And you need to, it's important to have these benchmarks and understand what simple linear or just one-dimensional models can accomplish before you invest a lot of effort in much more complicated models with deep neural networks. So let's just, to wrap up, let's just do the same exercise now instead of a numeric feature, which was the fraction of vaccinated people. Let's do a categorical feature. So for that, what I'm going to do, remember we had those Booleans that said which vaccines are used. So I'm going to make a categorical feature. And what I've done is I've basically made a 3-bit number. So this is just 2 to the power of 2, 2 to the power of 1, 2 to the power of 0 here. And so I'm basically making a bit mask, which says of these 3 vaccines, which are used in the country. So the AstraZeneca, Pfizer, and Sinovac vaccine. And so there could be 7 or 8 possible different values. It turns out that there's nothing with just a 1. So there's no country that only uses Sinovac and doesn't use either Pfizer or AstraZeneca as well. Okay, so there's 7 different values for this this category that I've created, and now I'm going to train a different random forest to try and predict that discrete category. And because it's a discrete classification problem, I'm using a classifier rather than the regressor that I used up here. Okay, in this case, I'm specifying a hyperparameter just to share an example of doing that. I'm training with the same data, but I've now got a different target. So I've redefined what an important feature is. Okay, so I'll just quickly kind of go through the same metrics. So the score 91. So before we got 95. So this is a harder problem. Let's look at the importance of the individual features and make that same plot that we had before. Okay, so this is very different. Before, we found there was just a single feature that was really dominating. And here we find actually the information in predicting which combination of these three vaccines are used is, you need to refer to a lot of different features. In fact, the one feature that seems to be most important is the fraction of the population that is in big cities. Okay, next is the amount of international trade, GDP, and so on like that. Remember, all of these features have been have been standardized. Although, in fact, for the random forest, since random forest only actually uses the ranking of values in a feature, this is one of the rare machine learning algorithms where that standardization actually isn't necessary. It doesn't make any difference. Okay, so I'm gonna stop there. We're in a few minutes over time, but I just wanted to kind of walk you through the steps that I normally do when I'm starting to work with a new data set and thinking about how to apply machine learning. So kind of first, I just start with kind of a summary of the features like this, using info and describe. Next, I will pick out to make some plots for small groups of features. You don't have to have just two. You can have 3 or 4. But you can't really use this sort of visual summary for for 20 or 50 or 100 features. And then I like to just restrict to the numerical features, get everything in a standard format so that it's easy to plug into lots of different machine learning algorithms. And then to get a sense of how many of the features are really necessary to explain the variation. Okay, we saw that 10 already gives us 90%. And then to take a deeper dive, I start defining some specific targets. And we did a real value target for regression or a discrete value target for a classification problem. And then just use a random forest. The reason I use random forest is because it's probably a local maximum in terms of interpretability and performance. You can really interpret the results for things like the feature importance. If you look inside a random forest, it basically boils down to a bunch of kind of yes/no questions that it asks about each observation. So it's like playing that 20 questions game where you have to guess something just by asking yes/no questions. So it's really interpretable what it's doing. And it's important that you start with some sort of benchmark. You have an idea of how something like random forest behaves and the performance you can get before you start using fancier methods with neural networks, for example. And then you can very quickly get some important insights about which features are important. And the important features are going to depend on the question you ask. So when we ask, how do we predict the fraction of the population vaccinated, we get a very different answer than if we ask to predict which vaccines a country is using. Okay, so I'm going to stop there. I see a question from Atalia. Yes, I will put this notebook on GitHub now. So. Okay, I see a question from Oleg.
Yeah, hi. I was wondering if, for example, in this example that you show, if your target value in the regression depends on another class of feature, for example, in these numerical features in an image, how would you combine the important information from an image and add it to the feature set to try and do a regression to get a target value?
So let me see if I understood your question. So you're imagining that the data you have are images, but you want to add additional features which give you some sort of properties of the image. So for example, if your images were of galaxies, maybe you want to add like the R magnitude and the ellipticity or something like that. Yeah. Yeah, so that's a good question. And so the name people give that is so-called feature engineering. And there's a pretty strong trend in machine learning to not do feature engineering. And that's mostly driven because, you know, researchers in machine learning, they want to use data from everywhere. So they want to use our data from astronomy. They want to use the you know, molecular genetics data from biology. They want to use you know, social media data from Facebook, and they're not experts in any of those types of data. And you need to be an expert. You need to know about the data that you're studying in order to do sensible feature engineering, right? So you know that, you know, magnitudes and ellipticities are important properties of a galaxy image. And so yeah, so I think you'll find that, you know, when you read papers coming from machine learning researchers, they say, well, you know, I'm not going to do any feature engineering because the raw data already contains all the information. So I'm just going to make a bigger neural network and throw it at a bigger computer and give it more data, and it's just going to learn those things anyway. But, you know, we as scientists, our data is actually pretty expensive to come by, and so it is actually important to do feature engineering. I think in particle physics and high energy physics, so like on Atlas experiments, they're kind of further along than we are in doing that and kind of hybridizing, taking the raw data plus some features. But generally, what people have done so far, it's either one or the other. Kind of either they do big neural networks with just the raw pixels, or else they will only do the features and kind of then use more traditional methods like random forest. But I think you're right that it's good to that it's good to think about hybrids, where you kind of help the neural network, for example, by giving it some important some things that you think are going to be useful. Yeah, it's a good question. Thanks. Any other questions now, where we have the notebook open? Yeah, we'll post this to, I will upload it to the GitHub repo. Did anyone, looking at your own data sets, come up with any surprises or interesting you learned? Something you learned? I saw several of you looked at the happiness index. So what makes us happy? Well, probably coffee breaks make us happy, right?
Yeah, I think they will bring some question for next session, probably, or in the Slack. Okay, so if there are no more questions,